A first-order differential equation has a slope field as shown in the diagram below. Determine the general differential equation that would yield this slope field. Well, the actual curves look like quadratics, and they're sad, they're this way. And we can also see that the gradient is 0 on x equals 2. So I'm thinking that something like y equals k, x minus 2 squared plus a constant. So let's make that a negative so that it's this way. So something of that form. And so that would give us something of the form, some constant, let's call it p, plus something times x, let's call it q, take away something times x squared. Now if we differentiate that, this constant would disappear, and so we'll get something of the q take away 2rx, so something linear. So I would probably state this as dy dx is equal to a minus bx. Slope field at point A, 1, 2, has a value of 0.5. Determine the equation for the curve y equals f of x containing the point A. So we have dy dx is equal to a minus bx. So we know that dy dx at 1, 2 is equal to a minus b, and that equals 0.5. Let's call that 1. But we also, as we noted before, noted dy dx, given that x equals 2, is equal to 0. Now that would be equal to a minus 2b. Let's call that equation 2. So if I do equation 2, take away equation 1, the a's disappear. No, actually, let's do it the other way around. Let's do it as 1, take away 2. The a's still disappear. Negative b, take away negative 2b, ends up being b. And then 0.5, take away 0, is 0.5. So b is 0.5, and that means that a is equal to 1. So we now have that dy dx is equal to 1 take away 0.5x. So y would be equal to x take away 0.25 x squared plus a constant. And we know the one we want goes through 1, 2, x is 1, y is 2. So 2 is equal to 1, take away 0.25, add c. 2 is going to be 0.75, add c, which gives us that c is equal to 1.25. So we have y is x, take away 0.25 x squared, add 1.25.